NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, everyone, and a very pleasant evening to you wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to our final remote edition of the 2020 Von Karman Lecture Series. Our series will return in January of 2021, but it's been quite a year, and I wanted to take a moment to thank all of you joining us from all over the world for this series. As we've gone from our public on-lab lectures to these remote editions, your patience and curiosity fueled us to find ways to continue to connect with you, our audience. As we say every single week, every single month, this is your space program. Over the past 11 months, we've said farewell to Spitzer, we've looked to Earth, explored how to become an engineer, and tonight we talk about the lessons of failure. Ever try? Ever fail? Try again. Fail again. Fail better. I think we could all relate to Samuel Beckett after this year. Joining us as co-host this evening is my colleague, Nikki Wyrick. Hiya, Nikki.
Hi, Brian. Thanks for having me tonight. I am very excited to be here, and I'm excited to take questions from all of you watching tonight. We want to make sure that you stay involved with our conversation this evening. So if you're watching on YouTube or Facebook Live, make sure you ask questions in the chat box, and our diligent social media team will bring in as many as they can to our talk tonight. If you don't see the chat box, make sure you reload. And as always, we want to remind you that this is your space program. So thanks for being involved tonight.
Thanks, Nikki. Thanks for joining us. As always, folks, if we run into any technical difficulty or small little failures, we ask your patience and stick with us. We'll get them sorted out as soon as we can. Now, our speaker tonight, discussing this wonderful topic, is Chief Engineer for NASA's Jet Propulsion Laboratory, as well as Chief Engineer for JPL's Engineering and Science Directorate. And I'm not going to go through all of the missions he's worked on because we'd be here all day, and we will be discussing quite a few of them throughout the evening. But as an engineering fellow, he has been designing, testing, and operating robotic spacecraft for nearly 40 years, including Galileo, Cassini, Magellan, and many Mars missions. Most recently, Rob helped create a team to design and build an emergency use ventilator specifically for the COVID-19 pandemic. Of all of his accolades, and there are many, my favorite is that he has a minor planet named after him. Please welcome Rob Manning. Hi, Rob.
Hey, Brian, thank you. What a great intro. I was like, who is that person you're talking about? Well, thank you very much. Thank you, Brian and Nikki. It's so great to be here, and it's so great to talk to everybody. This is a real treat.
Well, of course. Thank you for being with us tonight, particularly on this topic. We just said your resume is exemplary. You've gotten to work on so many missions, but I want to know, particularly for our students watching tonight, how did you originally get to JPL?
Great question. Well, I was very lucky. I was in fact, luck plays a role for all of our lives, of course, but I was very lucky in that I was a student at Caltech, which is just a few miles down the street from JPL. And they were looking in the early 80s, they were looking not for engineers because they had plenty of them in those days. They wanted some technicians. And I said, hey, I'm willing to take anything, just get my foot in the door. So I found myself as literally as a draftsman sitting on a drafting table with big plastic vellum sheets of schematics where I was drawing with a number 2 pencil and a nice, wonderful electric spinning eraser and drawing and erasing my mistakes in these electronic circuits that were going to be electronics that were going to ultimately fly on a mission called Galileo to Jupiter in a few years.
Well, I want to bring up image number 1 because we've got a great shot of JPL and also you, and you're letting somebody sit on a model of a rover. Who is that?
I know that. Well, that's actually a little robot that we put inside smaller robots. This is where we get our autonomy. We put small people inside small rovers. You probably knew that. This is the trick behind all of our autonomous systems. But no, this is my daughter, Colleen Manning, and when she was very young, I took her to our sandbox where we had been testing the Curiosity rover and little Sojourner rover, the very first Mars rover to explore the surface of another planet. I couldn't resist putting her. This is just a model of the rover, but I couldn't resist sitting her there. She was so light, and it was just it was a lot of fun. I mean, we had such an amazing experience, very much like the ventilator experience, where a small team of people did amazing things to make something happen, where we really tried to dare mighty things on Mars Pathfinder. It was quite an experience.
Well, we'll be bringing that phrase up again. And before we get into these examples, why is this? I mean, this topic is important for me. I know a lot of people it is. Why do you think this is important for not only our audience, but anybody walking down the street?
Well, this is a great question, Brian. One of the things. Well, first of all, this is a talk this is derived from a talk I give to engineers, and not just engineers, but all of our staff at JPL, to try to remind them that this is a very humanistic effort that we do. We try to do very hard things. I said earlier, trying to dare mighty things. This is one of our mantras. This is not just JPL; it's all of NASA. We're working at the behest of all of you taxpayers out there. Thank you very much. But our goal is to try to go out there and try to not just do something new and for the first time for its own sake, but try to do something for great reasons, so that we can push both the human and scientific understanding of our world and our universe. But in the process, though, I see a lot of people, including ourselves, our own engineers and scientists, being really hard on ourselves. It's interesting. In fact, there seems to be our whole culture right now. I'm sure all of you can comment on it. Is one of a lot of criticism and a lot of criticism. We're really hard on ourselves, and I see that our expectations for all of us seem to be so high, and yet we're always disappointed. And people seem to be so disappointed when we turn out to be just normal mortals, all of us. And it's not talking about engineers and scientists, but everybody. We put the bar very, very high, which is good, but we have to understand our own humility and humanity, that we are not perfect human beings, and that we as human beings need to learn. And one of the wonderful things about engineering, it's built on the idea of trial and error, that you can make mistakes, try something and build it again, see if you can get it, because no one is perfect. No matter how smart you think you are or how smart you would love to be, you have to understand that we do make mistakes, and we have to create an environment where mistakes can be made before everybody's watching you on CNN.
Well, that's kind of good to bring us up to our first talking point today. There was a time before people walked on the moon, and JPL had a big part of that, those proof of concept early on missions. And we're discussing the Ranger missions. Now, these proof of concept robotic missions, what were some of the first lessons that we learned from those? And we'll bring up our next image on that too.
Okay. Well, so the Rangers are really cool. And it's funny. I like talking about it because it's so long ago, people have actually forgotten what actually happened. And so JPL was very lucky to be in the right place at the right time, and was able to build the very first American satellite that was put into outer space as part of Explorer program. That was in the very late 50s. But fortunately, the director of JPL said, we'd love to get you, all of us, you NASA, you can work on getting people. All we want to do is kind of make robots and explore the scientific element. And while you're doing humans, we will send these little robots out there. And so NASA says, okay, fine, you can do that. So we started making these relatively, by today's standards, very inexpensive missions. And the Ranger program was the first in a series. But NASA said, listen, you guys, before you go to other planets, what we need to do, we're going to the moon. We want to send astronauts to land on the moon but before the decade is out. So early in 1960s, JPL set out to build a series of missions called the Ranger. What they were, these Ranger spacecraft were intended to aim for the moon. No one had been to the moon or even taken close-up pictures. So the idea was this spacecraft would be aimed like a bullet to the moon directly, and have a camera that was pointed down, go click, 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 taking pictures very quick, click, 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 and sent them back as fast as they can, up to the point where just before impact, the resolution on the images would expect to be very, very good. But that was a tall order because in those days we didn't have digital cameras. There were video cameras. They're called Vidicon tubes. It was really a television set. They're much like the old days in the 1960s and 50s of the big television screens, but made much smaller. And all that had to be put together and work properly. And so JPL had never navigated something that far across the solar system. They just really had thrown things out there before and hoped they weren't trying to aim. But now we were learning how to aim. We were trying to learn how to control something from Earth, and we really didn't have a lot of control over the joysticking of Earth from Earth. It was because even though it was only 3 seconds away by the speed of light, it still required a lot of autonomy on board the vehicle to be able to click through those actions very quickly as it approached the moon. So what happened? Well, they built a whole bunch of these. JPL built a whole bunch of these, and the first 5 over the course of about a little over a year, from late 1961 to late 62, they set 5 of these missions up one at a time every few months, and every single one of them failed. In fact, the first one was would be by today's standards very embarrassing. While it was sitting there inside the nose cone on the rocket pad, the solar panels, which are buttoned up like this, they inadvertently sent a command or caused a command to happen where the solar panels went boom and hit the wall of the nose cone. So it's like almost like a cartoon. Fortunately, they were able to take the nose cone off, climb up in the rocket, restow the solar panels, screw them back in, and then launch it. Well, fortunately, that was the good news. But the bad news, as soon as it went up there, it had all sorts of problems, and it didn't make it to the moon. That was number 1. Other problems happened on number 2. Other problems happened number 3. Other problems number 4. Another set of problems at number 5. And the last one just kind of, they keep missing the moon. In some cases, they hit the moon, went around the back, and bumped into the wrong part of the moon. Of course, on the backside of the moon, you can't send back to Earth. So it was a series of really horrible disasters. And after, you can imagine the lab director who came along, every few months, he would stand up in front of a wall of TV cameras and reporters and come up to the microphone and say, well, it didn't work again. And can you imagine at an institution, man, those engineers and people who are developing, how they felt? It was absolutely heartbreaking and frustrating because one of the problems is they didn't really understand why it was failing. So after 5 attempts, NASA says, stop. You're just wasting taxpayers' money. What are you doing? So JPL said, okay, what are we doing wrong here? And so JPL regrouped and rethought this through and said, okay, what would it take what are the things we're doing wrong? So JPL said to the engineers and project managers and the directors said to themselves, well, what could we do differently? And they realized there was a lot of lessons we can take. Even though we don't exactly know why all these things failed, we can take this much more seriously than we have. So JPL reorganized itself and added things like quality assurance and mission assurance and all sorts of patterns for ownership of design among individuals, because up to that, it's just a bunch of people working together. As my mentor John Cassani told me, people were falling over each other working on the spacecraft at the same time. It just no one knew what they were doing. So JPL reorganized itself, rethought it through, and try to make rethink the design. In fact, that's exactly what they did. They stood down for a good fraction of a year and reorganized itself. One of the things they did is, I don't know if you can see in that picture, there is a round ball on top. JPL, that was very audacious. They were going to make a lander, a balsa wood lander with a rocket that stopped it in midair, allowed it to crash on the surface of Mars and be able to make some seismic measurements on the surface of the moon. They got rid of that. They simplified. Listen, we don't need that anymore. We can just keep it simple. And they did. And they finally, after a year of redesigning the laboratory, redesigning how we're doing everything from scratch, they finally got it to work. It turns out the first attempt they tried after the start down actually didn't work. Everything worked fine, except by accident, while the vehicle launched, the camera took all of its pictures early due to a little bit of a spark in one of the connectors. And so another disaster. But fortunately, there are 3 more successes in a row that followed. And you know what? JPL breathed this huge sign of relief. Can you imagine? So imagine the reporters and others saying, who are these idiots? What are they doing? What do they do with our taxpayers' money? Why do they think they know what they're doing? And you know what? Because we had never done this before. We were being asked, and we were audacious enough as an institution to say, yes, we can. Can we? Yes, sure, we'll do it. And we'll learn. Well, the trouble with this system, we couldn't learn. We didn't know why they failed. So we worked hard to figure this out and make sure we understood what was going on and try to understand why it worked and why it wouldn't work. And we took this to heart, and we started the process of saying, listen, if we're going to fail, let's understand why we fail and not be afraid to stare failure directly in the face and learn from these mistakes.
So Ranger really was the first step in establishing a culture of learning from these moments. But something else that you said was talking about taking ownership.
Yes.
And that's something I think we're going to talk about throughout all these different missions that we're going to talk about, but taking ownership of the mission, of the goal, rather than just saying, do it this way, and this way. And you've talked to me about the differences between that.
Well, I'm a parent, and so one of the things that's so easy to do as a parent, in fact, not just parents, all of us, we're just wired to do it, is to tell people how to do their job. You tell them, do this. Okay, no, now move your mouse more to the right, then click. No, not now. Click again. And so people we're really tempted to want to give people, do the fishing for them, rather than teaching them how to fish and take ownership to become a fisher person. And so the idea of ownership is to give people the objective. Sure, show them how you do it. So show them how it's done. They can watch it, they can practice it, but then give them the space to figure out really how to get it done for the situation that they are in. And for us, that's called ownership. And aligning a group of people along a mission objective. And you could do that not just at a top level in terms of where, yes, we're going to send a mission to Mars. It's going to drive around another planet. But each piece can be done the same way. You can take each piece and say, listen, what is your mission? Well, my mission is to make a mobility system that can drive over these complicated rocky slopes in the surface of another planet. And so you take that as a mission as opposed to a series of tasks. Now you're more likely to take ownership with the outcome and and own the fact that, yes, my job is to make that happen. Yes, my job is to actually see it through. And so that is something that many of us, in fact, it's a very common belief that we have at JPL, that ownership is a key function of how you get something accomplished.
So NASA JPL, we're starting to take ownership. We're learning from these early lessons. We have some successes, and we're able to start daring mightier and mightier things. And the more we dare, the higher the risk of failure. And I want to go to our next image, and let's talk about the Mars Climate Orbiter.
Yes. Well, that's a great mission. It's a great example. I mean, to be honest with you, it's actually part of two missions. There were two missions. I had mentioned Mars Pathfinder earlier, but Mars Pathfinder was one of the first of a series of what was called at the time faster, better, cheaper missions, where the idea is to reduce the cost, reduce the overhead, try to be lean and mean, and try to do as much as you can with the smallest team you possibly can. Well, here, a wonderful team of very talented people, mind you, were designing two missions, an orbiter and a lander at the same time. And they were trying to capitalize on the similarities in those designs and put them together. In the process, they were both launched in the same launch window. Remember, you can only go to Mars every 26 months because you have to wait for the line. You can leave Earth orbit anytime you want to get to Mars orbit. But if you leave it anytime you want, chances are Mars won't be there when you get there. So you have to time your departure so that Mars will be there when you get there. And so that means every 26 months you can go. And the launch window is only a few weeks long. These two vehicles are on their way. This one was ahead of the lander, and this is called Mars Climate Orbiter. It was a wonderful mission. It was actually itself a mission to kind of help make up for some missions, another failure that had happened even earlier. But so this is what's interesting. This is what I love about this is when I talk to young people, I said, listen, you don't have to be a rocket scientist to be a rocket scientist. You can just look at this. You can look at this picture and says, what's about this? So imagine you're flying this thing from Earth to Mars. And those are solar panels you see sticking on the left there. It's on my right hand.
Actually.
Yeah, there we go.
I think we have.
You see it there? Okay, so look at that picture. So what do you see?
Yeah.
It's asymmetric, isn't it? So what do you see? You see that is a solar panel on one side. There's a big antenna that's that circular thing up on a boom, points back to Earth. It's a nice compact design. It's very elegant. But this asymmetric. So what does that mean? It means that if you're facing the sun, what does the sun do? The sun puts out light and shines on your vehicle. Well, light is like any other photons of light have momentum. When they hit the solar panels, they cause the solar panels to be a very tiny little force. That force just ever so slightly pushes the spacecraft to one side. So no problem. You just have to round it back again, right? Fire your thrusters on the vehicle or speed up a reaction wheel, or one of the two, to get the vehicle to straighten out. But eventually you have to keep firing these thrusters to keep the vehicle pointing the right way. Well, no problem. This was planned for. This was expected. There's nothing surprising about that. But these thrusters, in the process of doing what they were doing, not only rotate the vehicle, but ever so slightly gave the vehicle the tiniest little push to the left. You just move, just to the left. And so, but it's a very tiny amount. And this would happen every few days. Over time, it's the equivalent of force of literally, imagine a toilet paper square on your hand, pushing you to the left, ever so slightly, every day, all the time, just slightly pushing you. Where over the course of months, it turns out that small amount of force will push your vehicle to the left. Well, we're not stupid. We know those kinds of things could happen. So we just have to estimate how much that force is. So what we did, we had the software on board the vehicle tell software on the ground how much those thrusters were firing and how much it was pushing it. And we would then transfer that information to the navigation team, which would then figure out how much the vehicle has moved. Well, why do they need that? Why don't they just look at it? Well, this is another little detail. This is something that I try to encourage all of my friends at JPL, especially the new people at JPL, they all should know. How do you know where your spacecraft are in outer space? This is a great question. You know, how do you know? I mean, it goes way out there. You can't see it. You know, telescopes, you look out there, it just can't, it's not like a little dot, right? It's just, you can't even see it. It's no dot. It's too small to be a dot. And so the vehicle, we can ask what the vehicle knows. Well, how does the vehicle know? It looks back on Earth. It sees another little dot. Maybe a little Mars. Maybe it can kind of figure it out, but it doesn't have, these vehicles, this one couldn't have cameras to see where it is. No, the trick that we've used the radio. So what we do, we get transmitters on Earth and we send a little beep. Boop. The beep goes across space, bounces off the radio and antenna and the radio inside and bounces back to Earth, and we time it. And you know the speed of light because radio waves move at the speed of light, right? Everyone knows that. Mm-hmm. Click. Okay, now we know now we know how far away it is. Yes. Oh, and by the way, I can also send a tone to the spacecraft, and it can bounce the tone back. If the tone is higher when it comes back, it means it's coming toward you. If it's lower, it's going away, and you can tell how fast it is. So those two pieces of information should really help you figure out where your spacecraft is, right? Except for one detail. Right. Thanks. Yeah. Except that you know how far it is, but you don't know if it's over there or over there or over there, because the radio beams we're sending back are really big. And so it's like, but that's okay. We can figure out where it is because we've been counting how much it's been moving to the left because we've been getting this data. Well, what happened as the vehicle approached Mars, we discovered, and I think there's another picture coming up.
Image 5 here, actually.
Yeah. So as we're approaching Mars, this vehicle's approaching Mars, unbeknownst to us, we had underestimated the amount that Space Cool had moved to the left and in the wrong direction, the left. And so you imagine this, you're coming in from the lower right of your picture there. And as the vehicle's coming in, it's being pushed to the left, closer toward Mars, but you can't see it from Earth, right? What happened was, as the vehicle came around, got to the planet Mars, it fired its engines just before it got there. We could see the engines fire, and then it disappeared behind Mars. Early. I thought, whoa, who moved Mars? Mars wasn't supposed to be there. Mars, we're supposed to have plenty of time. We know where our spacecraft is. Mars, what's going on? And so we're like very nervous about that. But unfortunately, some minutes later, we're expecting to come around the back in this nice little loop you see here to put itself in a nice elliptical shaped orbit, because the engines put yourself in the orbit. Otherwise, we're just gone straight. So turns out we actually hit the top of atmosphere. This lander, and this orbiter became a lander by mistake. It hit the top of the atmosphere and broke up. What happened? Well, within a day or two, we figured out that the forces we were estimating from the spacecraft were in the units of pounds, English units of pounds, which is very common for propulsion people because they use English units for plumbing. You know, you get a 1-inch pipe, right? Quarter-inch pipe, 1 pound thruster. But our navigators do everything in metric. And so we expected this team expected to be metric, and so did everyone else. But of a very tiny little mistake that it wasn't corrected properly, and we were off by the difference between pounds and the metric version, which is newtons, a factor of 4.5. That's huge. We underestimated the force. We were 100 kilometers off course and in the wrong direction. And this orbiter became a lander. It was very embarrassing. It was very big news. We were shocked, all of us, how could we make something so stupid? I mean, it seems like a stupid mistake, right? But then you start thinking about, what's with this mistake? How do we make mistakes like this? Well, turns out we make those kind of mistakes all the time. It's a miscommunication, those kinds of things. It's not that we made the mistake that was wrong. It was that we didn't catch it, because all of us make thousands and thousands of mistakes, all human beings. That's what humans do, including the best engineers and scientists of the world. We're all human. We're all fallible. And so the trick is, how do you do something? How do you make something, $1 billion mission, say land a big $1 billion rover on the surface of Mars, where thousands of things have to work right? How is that possible? You just hire a bunch of great people? No. You don't just hire great people. You hire good people the best you can, but you can't expect being good to be good enough. And so what you need to do is test, check, find out before it's too late. Ask the questions. How do we really know that this is working? What if it doesn't work? Do we care? We really didn't ask those kinds of questions. And I felt, people like me really were very naive about this. And so I remember those days terribly. We were very hard, by the way, talk about being hard on each other. We were very hard on each other. We were, at first because can you imagine the emotional attachment of spending years trying to get these things to work? But, we learned. And guess what? We figured out how to do this better. And ever since, we have come up with new tricks. We've come up with new tricks that we've used and we'll be using again coming up here in January when Mars 2020, the Perseverance rover, arrives at Mars. We're going to use new tricks, and the new tricks allow us to see where our vehicle is in the plane of the sky. Rather than just guessing where it is over there, we can now see where it is exactly, because we're going to measure with our radio the angles between that and nearby quasars that have been tracked in the sky. So that's how we do it. And it's a new trick, and it's something we've used ever since. It had been invented before this mission, but we hadn't really put it to use in all of our missions, and it was just a wonderful addition. And now it's become just part of our new lessons, and we take this forward, and that's how we get ahead. We learn from our mistakes, get ourselves back up on the horse, and start again.
Well, something you talked about when we've been preparing for this show was I've always appreciated the grace and humility which you've talked about. You mentioned that Jay Leno made a joke about your. Yes. That can't be easy to deal with. But there's also this idea and something you brought up is, even with moments like this, there needs to be authentic confidence. There needs to be humility versus hubris.
Yeah, that's a tough thing, because think about it. We're hiring. So who are the people we're putting on these jobs? First of all, you have to say, well, they were in their elementary school. They were A students. Mm-hmm. A lot of them are A students. Their parents uh, thought they were pretty smart, and their siblings always would say, when a parent would ask a question, and the other siblings would say, I don't know, ask Susie, she knows all the answers. And and then you go, so Susie's sort of like on the spot, like, oh, I got to know these answers. All of us are in the same boat. We all try to know, but and it's important, by the way. You can't be afraid of everything. You can't be afraid of your shadow. You've got to be able to willing to get up in the morning, which is probably the hardest part of anybody's day, right? It's just waking up and getting out of bed, right? But then once you get going, get the energy going. See if you can make something happen. But don't let that confidence become that wonderful excitement of being successful turn into hubris and overconfidence. And that's the balancing act that we do. And it's important. I mean, this is one of the reasons I have to talk at JPL, because we see it, but even though these people, it's so easy for us to be hard on each other. And not just, and I don't mean at JPL, at NASA and together, but just in general. We all have to give these space. Imagine, for kids, especially for kids growing up today, think about this. Think about one mistake on a social networking is on there permanently. And it's like Bob Marley's chains, around your neck on the what's that Christmas show? You'll remember I'm talking about. It's
Robert Marley. I was like Bob Marley,
Robert
the
Marley.
whaler. Yeah,
Robert Marley. Robert Marley. Yes, Robert.
Christmas Carol.
Yeah, wrong.
Yes.
Yes, not that Bob Marley, not the Jamaican one. No. So no, it's these issues we have that in the old days, people will forget the mistakes you made. Now these mistakes feel like they have to wear them on their sleeves, and they don't want to, and it's something they're afraid of. And it's true for all of us. We've got to stop being so hard on each other and give ourselves a chance to make a mistake, create an environment where mistakes can be caught, if possible, and don't be hard on people just because they make a mistake. Listen, we don't want incompetence either. We don't want everyone making mistakes and just being going crazy. But we definitely need to allow people the space to fail and be human and learn from those mistakes and try to be better as people, because we are not perfect people. None of us are. No one is. We're just people. And so anyway, so that's where that comes. And I think the comment you made earlier about, it was actually after this other failure, Mars Polar Lander, I believe is when Jay Leno, who is, some of you may know, was a nighttime. I had the Tonight Show, and and I watched him one night, and I was trying to get away from my brain, away from the stress of work. And he said, well, just goes to show you don't have to be a rocket scientist to be a rocket scientist. After our embarrassing failures, and I was just like this, like, I read that he's right. First of all, he's right. You don't have to be a rocket scientist. But more importantly, at that point is that, yeah, he's actually making it's funny, but it is, we are human as anybody, and that's okay. And there's nothing wrong with being a human. And I think that's, all of us have to do it. And whether you're a student, where you're trying to learn and you're getting, and you get a bad report card or a bad grade on something, and it's not the end of the world. And mistakes are part of our very being. I can tell you, I have personally damaged. I'm not proud of this, but I've damaged no less than 3 Mars spacecraft before they launched, where they had to be repaired because of me, because I messed up, I screwed up. I told this to our HR department, and they went like, "Well, maybe we should have fired you." That's sort of we see a trend. But we were daring 90 things. It's hard to be right, and almost all these mistakes are mistakes that I share with other people, that I'm not happy that I made those mistakes, but I'm willing to share them, because it just tells the people that it can happen to any one of us. Even if the chief engineer of JPL can make a dumb mistake, then maybe I can here. But on the other hand, we've got to learn from these mistakes and try to make mistakes before. I don't recommend breaking Flight Harbor, by the way. It's very expensive. and very time consuming. And so I was very embarrassed and very, wasn't great. But I do tell people, why not, are you afraid of making mistakes? Are you afraid of being wrong? You can't be afraid of being wrong.
I think that's a great segue to or the last mission we're going to talk about tonight, because there are lots of questions out there, and we want to make sure that everybody, we can get as many of those in as possible. I want to go to image 7, and it's a successful mission, but curiosity, and we want to talk about the wheels. But really, what you were talking about, what is the difference between a lesson and a failure, and what is a failure of the imagination?
Yeah. So, I mean, certainly, you can, by the way, lessons can be positive as well as negative, but one of the things, and this is something that, almost always if we make a mistake or something, it's because there was something we didn't know. And one of the things that I try to remind people is to keep that humility running and keep that humility knob as high as you can go, even when you're being challenged to do something that other people aren't being challenged to do. And remember, by the way, is to listen to the quiet voices and make sure that the people who aren't as verbose as people like me, they can bring their voices to the table and remind us what the right things are to do. And because everybody knows something you don't know. In this case, this is a picture of Curiosity rover's wheels. Now, I am a bit partial to Curiosity. I was the chief engineer. It was a great team, and it was a huge challenge for project. We did make a lot of mistakes, but we fixed them and learned from them. But one in particular, one that I feel personally responsible for, is right there in this picture. If you look carefully in that picture, I don't know if folks can see it. There's that wheel on the right. This image was taken by a camera at the end of a robotic arm. And so it was able to look underneath the belly and take a picture. And we don't do that very often, but when we did, we looked and said, oh my goodness, what is going on here? Those holes in that wheel, not the kind of the rounded holes, but the holes on the right should not be there. What's going on? It's like somebody poked holes in the wheels. And people like me instantly knew what was going on. And because I'd seen similar things going wrong in testing we had done before we launched it, years before. In fact, at least a couple of years, and in time, at a time when I could have done something about it and fixed it. But what happened was we didn't use our imagination. This is a case where, it's hard to be smart and hard to predict the future. Predicting the future is very difficult. I forget what Yogi Berra said, a version of that, but it is very hard. But even so, we should have put all the two and two together. So what had happened was we had seen that the wheels in our test bed, the wheels had been damaged, and so we talked ourselves into thinking, well, listen, our test program for these wheels was pretty darn good. We had a wheel that went over these very sharp rocks. I don't know if you know this. So where Curiosity landed in a lake bed, it's clays everywhere, and there are rocks sitting in the clay bed. And those rocks are sitting there. They're bound hard into this lake bed. And it turns out, even though there's air is only 1% the density of Earth, it's very, very thin. There's wind on Mars. It's not huge. And it's kind you can barely feel, but it's enough to get little tiny particles of dust to bounce along the surface. It's called siltation. It bounces over the surface, and it can wear these rocks into these incredibly sharp, fine edges, almost like knife edges. They're called ventifacts. This happens on Earth too. But these rocks are basalts, lava rocks. They're really hard. And but we knew that happened because we saw that same thing happen some years back with Spirit. When it landed on Mars, we were driving around. I was like, well, look at those sharp rocks. Those are airbag eaters. I told myself and the team. And so we were designing this wheel. We want to be sharp-handed. We work fine with these rocks. Well, we tested these things on rocks, but guess what? In our test bed, we put the rocks down. We didn't glue them down. And so, and there's another thing we did. That's one thing we did wrong. The other thing we did wrong, I might just grab, since I have it here handy, I happen to have Curiosity rover model right here. I just happen to have it. I sleep with it at night. It's kind of nice. So it's got these wheels here, and so what happens? So look at this. So these wheels, look at how they move around this mobility system. These wheels go up and down. They move over rocks. The whole thing moves. But we designed all three wheels to move at the same speed. All three, thinking that was the right thing to do. And that works fine for small rovers, but when we scaled up this bigger rover, we weren't really thinking, were we? It turns out, if you're trying to drive, what this wheel was trying to drive over a bigger rock, and these back wheels are going at a fixed constant speed, but this wheel is going the same speed. This wheel needs to go faster to go over the rock. Well, but it wasn't. It was going the same speed. So basically, these back wheels are pushing the front wheel and the side wheels faster than they can keep up. And now if you get these rocks that are buried in clay with sharp edges and sharp, like a bear claw, you're just going to rip these aluminum wheels like a Coca-Cola can. And that's basically what happened with us, and to my dismay. And I was kicking myself for not putting those two pieces together. That we weren't thinking about. We're going to a clay. We're going to a place with water, right? And that means it's going to be clays. What's clays do? Clays lock rocks down. What do rocks do? They make sharp points. They just don't lie there in the ground, because when we were testing the wheels over sharp rocks, these rocks would bend over. As the wheels turned over, the points would move with it, and they weren't damaging the rocks. And so we underestimated just how bad Mars really could be. So our imaginations were not sufficient. We didn't put all the pieces together to allow ourselves to appreciate what could actually arise when we get to Mars. And yet all the ingredients for figuring that out were there 2 years before we launched. So I kicked myself for not thinking that through or making a bigger issue out of it.
I always appreciate your accountability and your acceptance into these. And I think that's a big part of what you have to do, but also in everyday life. We're going to open it up to the audience. They've got a lot of questions. So I'm going to send it over to Nikki. How's it looking out there, Nikki?
We've got a ton of interest online, Rob, especially with our students. I know that's a big passion project of yours. We've got quite a few people who are asking for advice, how to get jobs at JPL. For instance, Kevin on YouTube has asked, what are your suggestions for early career scientists and engineers wanting to pivot towards getting involved in future space-related projects?
Oh, well, a little luck doesn't hurt, okay? But I tell you, I think there is something about people in this line of work that is important. First of all, you're unlikely, unless you start your own company, to get rich doing this work. But you will be greatly enriched with the magic of exploration, the magic of trying hard things and being at least attempting to be successful. I think the biggest thing I would recommend for anybody, and they all seem to have this, all the people who come to this, whether it's JPL or NASA, they all share something. They share a deep passion and interest and curiosity in how things work. They want to be part of it. They are patient. They're willing to learn. They're not afraid of not knowing, at least at first. And I think that a career that starts off where, obviously for the kind of work we do, it's really hard to take a class on how to build these things and how to do these kinds of missions. However, there is plenty of room to really, you can learn that on the job. The hard part is learning the fundamentals, knowing the math, physics, understanding communications theory, understanding thermodynamics, understanding the basics of how physics works, and the lowest level of engineering works, how electronics works, how computers work fundamentally, not just that how the apps work, but what's going on inside these complicated machines that we build, and try to understand those and try to get an authentic understanding of that lower level, because it'll take a lifetime to really learn about all these details about these things. That's okay. You'll learn that on the job. They'll pay you to figure that out. We'll pay you to do that. But we really need you to be a person of curiosity and passion and interest, with a spark and a willingness to learn and ask questions.
That's really great to hear. And, some people online have also been asking a little bit more specific questions. For instance, Jeremiah was asking about what type of programs we use and how Jeremiah can learn more about those launch programs or other types of projects. How do we do those calculations and those simulations for those type of things?
Oh, I mean, how do we? Yeah, good question. I've wondered that for years. But the wonderful thing about understanding how things work is that once you understand, you can create models of these worlds. For example, the incredibly exciting sequence of steps that require that the vehicle needs to transform in automatically all by itself on landing day to land these big expensive missions on another planet. Is almost impossible to test here on this planet. It really is. You can test pieces. I can go up to 130,000 feet or higher and inflate a full-scale parachute in front of a rocket and test out the parachute that way. I can take these wheels and drive them on an environment that looks a lot like Mars and do it right. And we do it right now. And do the testing properly. We can do almost all these things in bits and pieces, but we can't really test all these things as a system. You can't do entry descent landing, a Mars entry descent landing on this planet. Why? Because not just the gravity, but the atmosphere is so much thicker. It's a very different system. On Mars, the atmosphere is the equivalent to try to land on a mountain that's really 130 feet high above the surface. There are no mountains that high. That's many times higher than Mount Everest. And so there's no real way to do it. So instead, we have to build computer simulations. And we have to use the laws of physics interacting with models of the atmosphere, of the surface, of how, and understanding how radar signals come out of radios come out of a radar and how it bounces off of rocks and slopes and back into the radar, and simulate all of those pieces to try to really get yourself a good understanding of whether or not you think this thing's going to work or not. It's very dangerous because we can't test it. I mean, imagine this. Imagine the first time you flew an airplane is when you loaded up all the passengers. No, don't do that. But we have no choice. So we have to have models. We have to have computer simulations. We have to understand the mass properties of a spacecraft in space, its momentum, how much its angular momentum it has in space, so we can fire simulated rockets that push it this way and push it that way, so we can aim its solar panels properly at the sun. And you can do those kinds of things, but it's very tedious work. I'm telling you, this stuff is tedious work. Almost all the engineers who come here are very excited. First thing we do is to give them something massively tedious to do because it's so easy to get it wrong. They have to go through this detail to figure out and have the perseverance, which is a key attribute of success in this business, to go through and struggle through it and fight.
With so many opportunities and points of failure possibility, it's astounding how much success that you and JPL have had. And Canon on YouTube wants to know, how does it feel to have a mission in which thousands of things can go wrong and have it turn out to be a complete success? How does that feel?
Well, it's usually a big surprise. I tell you. So I like to tell people all this all the time. Is so you've seen us there in our polo shirts, or in case of Curiosity Landing was these light blue shirts, and we're all like going screaming up and down. Your faces are turning red. People are crying. Are they relieved? No, I mean, are they happy? No, they're not happy. They're relieved. It's just like because even up until that very moment, in fact, for me, sometimes for days after, you are constantly thinking, what did I forget? What did I miss? What's the piece of the puzzle that I didn't think of? And and that's what we want people to do. We want them to be constantly think about, what did we miss? What did I not do right? What mistake did I make? And so when you put all these pieces together, in fact, it's really even hard to know as you're getting closer and closer. You think, well, am I done? Well, you're never really done until the thing lands. You're constantly thinking about those things, and that's a good thing. It's a good thing. You sort of know. I have to admit, people ask me, say, Rob, how do I know when we're actually done? We seem to be testing and testing and testing. Are we getting done? I says, well, here's the question: are we learning anything new? If we're still testing and we're not learning anything new, and it seems to be doing what we want it to do, we might very well be on the plateau. It's very much like, you imagine you're climbing Mount Everest, right? You're climbing the mountain, going up higher and higher and higher. But you can't see where the summit is. It's all murky and there's clouds everywhere. But the slope is sort of leveling off. You're getting up this. It was still very steep, but eventually it gets flatter and flatter and flatter. And you go like, but you really can't see if there's another peak ahead of you. But you just say, you know what? I think I might be there. We're at the flat spot. We're at the sweet spot. Maybe we're there, but you never know for sure.
It's great that we can have these conversations about all this knowledge that you're passing on and all the information that you're learning from your own experience at JPL. And Tio on YouTube wants to know, how does JPL and NASA work to pass on generational knowledge and make sure new employees don't make the same mistakes as their predecessors?
Oh, what a great question. We have a chief knowledge officer who works with me, and she's chartered with figuring out how do we do that. I tell you, it's really hard because a lot of it is storytelling. I mean, a lot of things we do. For example, we do, because we're engineers, right? Okay, well, we learned this lesson, so we write down new rules, right? New rules, a whole little rule book that goes longer. It's longer and longer of all the things. Well, remember, you can't do this. You got to do this. You can't do this. You got to do this. But there was trouble with that style, and that's something we do a lot. Is that it misses the story, the narrative, and in some sense, the way that we really learn is by living vicariously through the experiences of others, previous generations, standing on shoulders of giants, of people who tried and succeeded, and those who tried and failed. And it's really hard to do, because guess what? We also have real jobs to do, and we don't have a lot of time. And it's really now in the time of Zoom and WebEx and Teams, it's very difficult to have those casual water cooler conversations that allow people to tell the stories. So this is a really difficult time, and so it's really hard. I'll be honest with you, I'm not sure we know how to answer that question. We're still figuring it out.
Well, I love that your attitude is that we're still figuring it out. We still get to work together on these things and make improvements and learn together. Ryukachu on YouTube asks us, what's a project that's on the horizon that you're incredibly excited about? Either something right now or something that's not built yet, but's coming in the future.
Oh, we have a bunch of them. It's really exciting. The great thing about being the lab's chief engineer, I can see all the things that are going on. There's one mission we're building, which is going to go visit an asteroid out in the asteroid belt called Psyche, and this is a rock in outer space that we think was once a planetesimal, a small planet, and something. Most planets have an iron core, right? Well, something we think, we can tell from our telescopes on Earth, we think that something wiped away all the rock and left this big iron ball, this massive iron ball in the middle of space. And we think that's what it is. We're going to send a spaceship out there to go visit and confirm that's exactly what that is. If that's the case, that's the largest chunk of available iron you would find anywhere in our solar system. It's amazing. We have another mission that's going to go in orbit around Jupiter. Jupiter, very scary place to fly around, it turns out, because it's got radiation from this. Jupiter has this amazing magnetic field, which is beautiful and powerful. But it's also got moons that squirt up atoms from volcanoes, Io in particular, and that those particles get accelerated because they're charged up, and they start racing around from pole to pole and around Jupiter, making this a very dangerous place to fly. It's very dangerous for people. It's even more dangerous for people. But if you're lucky, you can make electronics and put them inside vaults of lead and send them to Jupiter. But what we're going to do is go to orbit and around Jupiter, but not to see Jupiter. We want to go visit and fly by Europa. Europa is this moon. It's a very large moon. It's smaller than our moon, but it's unlike any other place, with possible exception Enceladus. It's a big iceberg, giant ball of ice. But underneath many kilometers of ice are these massive oceans, and below the oceans is a rocky center. So it's almost like Antarctica, except it's the whole moon. In fact, there's more liquid water on that little moon than all of Earth. In fact, maybe 3 times or more water on that little moon than Earth. In fact, that water could be a very habitable place, could very well be a habitable place for life as we might know it on this planet, where the inside's nice and warm, heated from the tidal forces of Jupiter, and the outside's very cold, but protects the life. The ice protects the life inside from that horrible radiation environment. So that's a very exciting mission. And of course, we get another one. We've got a mission on its way to Mars right this second. Mars 2020 Perseverance rover, I mentioned this before, is on its way. February 18th, I believe, right? Is landing on Mars around lunchtime, and I'm going to be watching, and hope all of you will too. It's a rover, look very much like Curiosity, but unlike Curiosity, this vehicle is going to collect samples, pristine samples, and put them very carefully in these very specially designed tubes to hold them, seal them tight, and with no trace of human contamination or biological or chemical contamination because of how we're doing it, very surgically on the surface of Mars. Once those tubes are collected, another mission, which is just starting now, called Mars Sample Return, is going to land another vehicle. It's going to send a rover built by Europe to go collect those sample tubes, bring them back to a rocket made by NASA's Marshall Space Flight Center, and launch it into space, and will be then picked up by another system built by NASA's Goddard, and it's attached to a big European biggest spacecraft ever sent to Mars, that will then fly back to Earth and drop off a space capsule that NASA Langley and NASA Ames Research Center have put together, and drop these samples back to Earth. And this is the later part of this decade, in early 2030, around 2030, but that's our hope, and this is what's going on. So incredible excitement, lots of amazing things. And that's just the tip of an iceberg too.
Well, looks like we've got time for one last question. Nikki, one last question for Rob.
So last question of the night, Owen on Facebook asks, loved your book, Rob. Are you planning a sequel about Perseverance?
Oh, thank you very much. I'm glad you like my book. I'm not allowed to advertise it, but I tell you, it's a joy to capture these stories, and I don't know if I'm going to write. I'm not going to write them for Perseverance. I'm going to leave that to the Perseverance team to tell their stories. And capturing these stories is just so essential for not just for the public to see what really goes on behind the scenes, but also to share with our own staff and the next generation of future space explorers that many of you are, I presume.
Thank you for sharing your stories with us tonight, Rob.
Sure.
That is all the time we have for questions. I want to thank Rob for joining us and discussing this often neglected topic. As a reminder to our audience, we do not have a lecture in December, but we will see you again in January when we discuss spacecraft origami. I'd like to give a huge thank you to everyone on our crew, every single person who is involved in these talks, for their ingenuity and their drive in keeping these monthly talks going this past year. My final thank you does go out to you, the audience, from all over the world. This is your lecture series. We're happy to bring it to you every month. Thank you for taking the time to join us. And if you missed one of our talks, you can revisit our Von Karman talks from the past 5 years. They're all available on JPL's YouTube page. There's a whole playlist for them, so you can go find them. Before we go, I'd like to pass it over to Rob one last time to give us a reminder of why we shouldn't be so hard on ourselves.
Well, Brian, this is great. Nikki, Brian, this is fabulous. Thank you for inviting me. I have to say, I learned one thing from my mentor, John Cassani, who told a story about one of JPL's the early NASA pioneers named Homer Stewart, who said there, remember there's 10 most important words that they told each other. One is, I don't know. I'm sorry. We can fix it. And so I think those kinds of expressions are very important. I think we need to know that we don't know. And by the way, it's not just individuals that we should be not afraid to be honest about our own mistakes, but our bosses have to also remember to let the people who work for them, we need to give them the space to succeed, and all of us need to give us this place to succeed by learning, testing, trying things out, and before make the mistakes before it's live in front of millions of people on national television.
Thank you again for joining us, Rob, and thank you, folks. Stay safe, stay kind, and we'll see you in January.